So our learning target for our first section is we're going to be able to apply trig ratios and special right triangle properties to solve problems. Some of them may be word problems. Go ahead and start the warm-up question. Use your Pythagorean theorem to find our missing hypotenuse. All right, what's the length of our hypotenuse? 13, right? We have 5 squared plus 12 squared equals c squared. So we get 169 equals c squared. C equals 13. So when in doubt, don't forget Pythagorean theorem questions will come up as we go through this unit. It's just hard to avoid, right, when we're talking about right triangles. Let's go ahead and make sure we clearly identify what sine, cosine, and tangent are. We're still going to refer to SOHCAHTOA to help us out a little bit as we memorize these. Hopefully this acronym helps you. Instead of necessarily labeling angles, though, with like A, B's, and C's, we oftentimes will use Greek symbols. This is the Greek symbol for theta. So that identifies that that is the angle that we are focusing on. So I always like to circle our reference angle and label our opposite, our adjacent, and our hypotenuse. Remember, your hypotenuse is always the side across from your right angle. It's your longest side. The adjacent side, well, that's the side that is right next to your reference angle, and then the opposite is your side. So sine, opposite over hypotenuse. Now we've got these other lines down here, right? So this right here stands for cosecant. And cosecant is partnered with sine. S and C go together. It is just the reciprocal value. So this is hypotenuse over opposite. Or you can also think of it as 1 over the sine of theta. They mean the same thing, right? They're just reciprocals of each other. So these two are closely related, right? Sine and cosecant. Cosine is adjacent over hypotenuse. Therefore, secant, that's what this stands for, secant. So again, a C is paired with an S. It is, again, just the reciprocal. Hypotenuse over adjacent, or you can think of it as 1 divided by the cosine of theta. And then last, we have tangent, which is opposite over adjacent. That is partnered with what's called cotangent, which is adjacent divided by opposite, or 1 divided by the tangent of theta. So really, these kind of are the new things that we would have introduced in this section in Algebra 2 that's new from geometry. And we won't use them a lot. We'll use them maybe a little bit, right? If you're calculating these, it's very easy to calculate these as well. But once you get to trig, if you take trigonometry after pre-calculus, we use them interchangeably. We use like all 6 of these. So really, this year is just about introducing them to you so that you're not overwhelmed if you take more math later. So let's get our first example out of the way here. If I'm given a sine of theta, so here's my theta, my reference angle, I'll label my opposite, my adjacent, my hypotenuse. So if I know this sine of theta is 2 over 3, now I just need to figure out what all of the other trig ratios are. In order to do that, though, right, I need to figure out what my adjacent value is. So what should I use? Pythagorean theorem. Yep. 2 squared plus adjacent squared equals 3 squared. So I get 9, subtract 4. So my adjacent side is the square root of 5. Right, we just use our Pythagorean theorem to get that. So if I know sine is 2/3, what's cosecant? 3 halves, right? I just flip it, right? That's the nice thing about those. We don't have to overthink those too much. Let's look at our next one, cosine. Shout it out, feel confident.
The square root of 5.
Thank you. The square root of 5 over 3, right? Our adjacent side is the square root of 5. Our hypotenuse is 3. Now let's calculate secant. So for secant, all I have to do is flip these over.
Oh, but you can't have it.
Oh, you caught it.
No.
This is why, right? This is also the big leap from geometry, is we're not calculating a lot of things in decimals, right? Things are going to have to stay in their radical form, which means we have to remember some of our rules, like we're not allowed to have the square root in the denominator. We must rationalize it. So we end up with 3 square root of 5 divided by 5 for secant. Yes, indeed. All right, our last two, the tangent of theta. 2 over the square root of 5. And we run into that same problem where we have a radical in the denominator. So I get 2 square root of 5 over 5. And then cotangent, I'm not going to look at my final answer over here. I'm going to look at it just right here, right? I just flip these over. Square root of 5 over 2. Or you can just look at your triangle and know if tangent is opposite over adjacent, then cotangent is adjacent over opposite. Questions? Probably like the first thing I'll ask you to do on your homework is just give me the 6 trig identities for a particular triangle. All right, let's talk special right triangles, right? They are special. There are some of these special angles that we will talk about quite a lot as we go through this unit. So our first one is a 30, 60, 90 triangle. Now what I'd like you to do is just draw a smaller triangle off to the side. That's also 30, 60, right? Because similar triangles are going to have similar properties. So if we talk about, okay, here we're just going to write the side lengths for this particular triangle. If I know that across from my 30 is just 1 unit, whatever that unit is, 1 centimeter, 1 foot, whatever. Across from my 60 is the square root of 3, 1.7, whatever it ends up being. And then across from my 90 is 2. So a 30, 60, 90 triangle is in proportion, has a ratio of 1 to the square root of 3 to 2. So every 30, 60, 90 triangle is going to have these same properties. So over here, instead of just writing it as 1 square root of 3, 2, right, we want to make sure it's for every size triangle that's 30, 60, 90. I make it x, or 1x, x square root of 3, 2x. So these are the same proportions, just now we put a variable attached to them to kind of figure this stuff out. Questions? Okay. Our next special right triangle is the 45, 45, 90. It is an isosceles triangle, right? Those two sides are congruent, so I can put little tick marks there. Let's again draw another little triangle off to the side. So if the legs of this right triangle are 1 and 1, then my hypotenuse is the square root of 2. Right? If I were to do this with the Pythagorean theorem, 1 squared plus 1 squared equals c squared, take my square root. So these proportions, right, are 1 to 1 to square root of 2. So I would label this as x square root of 2. Let's start filling out a little table below of our sine, cosine, and tangent. I I want you to be using these smaller triangles that we kind of drew off to the side. I'll show you what I mean. So for 30 degrees, I'm going to look back over here. The sine is opposite over hypotenuse. So 1/2. The cosine is adjacent over hypotenuse, the square root of 3 over 2. And then tangent is opposite over adjacent. So 1 over the square root of 3, which unfortunately, right, that one, I'm going to have to simplify. I get the square root of 3 over 3. Questions on how I got those? I'd like you to do these two. Do these two rows yourself. Using those small triangles that have side lengths of 1 to help you figure out what those values are. Don't worry about the 0 degrees and 90 degrees. We'll do that in a second. Use this one. I don't want X's in there. I know. All right, let's go over these. So for 45 degrees, I'm going to look at my smaller angle, right? So sine is opposite over hypotenuse, so 1 over the square root of 2, but then I got to get rid of that square root of 2 in the denominator. So I get the square root of 2 over 2. Same thing for cosine. And then for tangent, 1 over 1, you can write it as 1 over 1 if you want, or just 1. 60 degrees. Anybody want to shout out what they got for the sine? Square root of 3 over 2. So then what is the cosine? 1/2, right? Do we see this relationship up here, right? Look at our sine and our cosine for 30 degrees and how that compares to the sine cosine for our 60 degrees. We're working our way towards building what's called the unit circle, which is like the foundation of all trigonometry and how we study it. We're working our way there. And then the tangent of 60 degrees is the square root of 3 over 1. If you want to keep that placeholder, square root of 3 over 1, feel free to. Now for 0 and 90 degrees, let's use our calculators. Okay? Eventually, like I said, we're leading towards this unit circle, but let's use our calculators to figure out what is the sine of 0? What is the cosine of 90 degrees? So fill out this table using your calculator. Make sure you're still in degree mode. I assume you all are at this point. You should get some ones, some zeros, some errors. Get some error messages as we went around. All right, what is the sine of 0? 0. What is the cosine of 0? Oh, yeah. And then what's tangent?
0.
How about the sine of 90?
1.
Cosine?
0.
Okay. The tangent is sine divided by cosine. So look here, right? Sine divided by cosine. 0 divided by 1 is 0. 1 divided by 0, undefined. So you probably got an error message on your calculator. In our very last section of the unit, we will graph, and we will kind of see why tangent is undefined at certain angles. Okay, but that's really, I just wanted us to use our calculators. I do have a Quizlet to help you memorize this. It is linked on Google Classroom. If you memorize these main angles and all of their trig functions, this unit will be much easier for you. So I highly encourage you to memorize this table of values. We have time, maybe I'll have us do some quick Quizlet practice, but it is worth memorizing these special angles. Let's go ahead and start working on some example problems now that we have all this knowledge. These two are special right triangle questions, but they are the most challenging ones that are out there, okay? The reason being, I have a 30, 60, 90 here. But across from my 30 is x, that's kind of what I wanted, right? But across from my 60 is 6, right? Shouldn't this have a radical 3 in it somewhere, right? We just covered our special right triangles, but unfortunately, right, that's not how it always works. So there's a couple different ways to do this. You can do this the algebraic way, which is what I will show you, or you can do it the pattern recognition way, using your number sense, shortening this cycle. Because we have to figure out, I have this, and if I multiply this by the square root of 3, I get 6. So I have to think to myself, x times the square root of 3 is equal to 6. Now let's go through and solve this algebraically, and maybe we'll start to see, right, the pattern will reveal itself to us. How do I solve this for x? I divide, right? These two are being multiplied, so I divide. So I get x is equal to 6 divided by the square root of 3. We're back to having a radical in the denominator, so we're going to get rid of that. So I get 6 square root of 3 over 3. 6 divided by 3 is 2. So my value over here is 2 square root of 3. Notice how, right? Now I know, right, the square root of 3 times the square root of 3 is 3. So if I'm going to take this and multiply it by the square root of 3, and I wind up with a whole number, I really just have to think to myself, what is 6 divided by 3? Right? That's going to tell me the number that's out front of the radical 3 here. If you don't see the pattern, don't worry about it. The algebraic method of solving will work for you every time as well. Okay? It's just, that's a shortcut. The whole point of special right triangles is to be a shortcut for you. But I know when we're first learning, it's not necessarily the case. So we have 2 radical 3, 6. This value of y, right, across, whatever is across from your 30, you simply double it. And that tells you your hypotenuse. So if I multiply 2 times 2 square root of 3, then this side of my triangle, my hypotenuse, is 4 square root of 3. It is, right? Questions on where these 3 came from? How we got all of our sides, just by using special right triangles. We're going to do some practice with it, okay? All right, now our next one, this is another challenging one because I have a 45, 45, 90. So this should be x square root of 2. I have to figure out what number can x be so that if I multiply it by the square root of 2, I get 10. Anybody have a guess? think about it. It's worth thinking about for a second. You know, end of the day, trade on. Over here we had a square root of 3. Over here we should have a square root of 2. Let's solve it. I'm going to take this, and if I take x and I multiply by the square root of 2, I should get out 10. Divide by the square root of 2. Get rid of that denominator. I get 5 square root of 2. Everybody kind of see it, maybe a little bit. What we're going to do is we're going to pause for a second and do some practice with special right triangles. This is kind of the same look I got from the last class. So I'm handing out a maze. It's on special right triangles, so it's going to use 30, 60, 90, 45, 45, 90. Feel free to work by yourself or with somebody else. Make sure you start where it says start. I had a student last class that started in the wrong spot, so make sure you start where it says start. There's a couple of tricky ones on here, but then there's also some kind of straightforward ones, so don't skip over those. I'll be walking around to help.